Hi again, everyone. My name is Yam Habib. I build some models for solving image captioning tasks. The image captioning task, I think you already know it. It's the task of describing the content, the objects of the within an image, the content of the image, the attributes of the objects, and the relationship between different objects in the same image. For this task, I used the Flickr 8K dataset. It has 8,000 images with, for each image, we have 5 different captions in most of the cases. Let's start like by processing the data. So for first, like we process our captions. For each caption, we add a start and end tokens. We split the caption into words. We keep the words that has the alphabet letters, so we don't keep the numbers and like punctuation marks and something like that. And we delete the empty words. Also, we add, this is padding, a padding token at the end of the captions. So we make our captions have the same length. We vectorize our words, and then we build an index to word and word to index dictionaries. This is the process, and these are the functions that implemented this idea. This is the final look of our data set. So this is, we have an image. For each image, like this is the same image, we have different captions. We add the start, the end, and the padding tokens, and then we tokenize them. How we tokenize them? Just we assign a number for each one of the word after sorting the tokens. So, for example, start has number 2 because it occurs more frequently in our data set. We select our data set 90% and 10%. I know that these percentage are not the optimal, but because the data set has it's not like large enough, so this is why I needed more data to train the models. And also the models are somehow they are large, so they need like enough data to fit. Here we're defining image dataset object to just to build a data loader to get our batches and build our batches and build them. For images, I use like I build the image features from an ResNet 34. The idea is I took ResNet 34, I get the 4th layer, then I like run this model on our images and save the result into 2 different files. So each time when I'm going to train my models, I just get the feature vector immediately without putting the model in like in the GPU or something like that. This is helps us to save a lot of training time. Why I choose ResNet 34? The reason actually is just because I don't want to put any extra layer between the image feature, the feature vector of the image, and our model. And since my model that won't like that will generate the captions, I choose like 512 for the dimension of the model. So the ResNet 34 has give me this dimensions already. So this is why I preferred ResNet 34. And later I will explain it more about this idea. And here I built the encoded image dataset. So now I have my dataset is ready. I have the image, the feature vector of the images are stored on my disk. I can get them immediately with the captions with the tokens of the captions, like this. I build 3 different models, starting from the basic idea of the image captioning, which is using the RNN, recurrent neural network. I used the long short-term memory recurrent neural network with the attention mechanism. I think you know what is the attention, but a brief description. The attention mechanism is just, we have tokens, like for example, here we know we want to start generating. Each time when we want to generate a word, our attention mechanism will help the decoder, which is here the LSTM, will help the decoder to focus on a part of the image, not all the information of the image. This increase the accuracy and like make the model stable in training, in the training process. How we generate these attentions? It's the idea of a query and a key. The query that we have, it's the word that we want to generate. So the decoder wants to generate something, and he has a query. This query is the last hidden state. From this query, we get the key. The key, we get it from the image. We, from the query and from the key, we generate an attention value. This attention value tells us how much our model should concentrate on this feature from the image. After generating all these values, we make a softmax to make to move it more like them like a distribution, and then we have a context vector. We build the context vector as a sum of the keys of the feature vector of the image, and we weight each vector by this alpha value. So in this way, our model still look at all the image, but he have some parts like more important than others. This is the implementation of the attention. It's pretty straightforward as here. And then the decoder, which is an LSTM model. We built our model. Here have our hyperparameters. We train it. Here, the last time I ran the training, it's like at the 4th epoch, and it just started to overfit. So I stopped the training process because it has it takes some time. We save our model to the disk. We loaded our model and we tried it. For example, a dog is running on the grass. Of course, the model isn't good enough because I think the size of the model, the size of the model and the size of the data set. I think if we want to improve the accuracy, we need to increase the dimension of the models, and I think we might need to use better encoder like ResNet 50 or 102, I think. For measuring the performance of our model, we use Blue Score. Briefly, Blue Score is a metric that avoid the false, I can say the false precision. For example, if our model here just output like the word dog all the time, so like 6 times dog, our normal precision would give us 100%. But the Blue Score, it just consider how many times or the maximum time that dog appear in the reference sentences. And according to that, he called the accuracy. So for example, even if we have here 5 times dog, if the maximum number that the word dog appears in any of the reference sentences is, for example, 2, so our precision would be 50. Or for example, if we have all dogs, our precision would be like 2 to 5. So this is the idea of the blue score. And from what I read in recent papers, I think it's the most common metrics to use for image captioning. I know that there are different like CIDR and TF-IDF, but I think a blue score gives us like a good metric to measure our model. And here we printed like the blue score for like 1 gram, 2 gram, 3 gram, and 4 gram, and these are the results. For 1 gram, the result is medium. For the others, it's bad, and that's because the model can't like it has the good words, but the sentence as a whole isn't good enough. This is why like I moved to another model, which is the transformer. Basically, transformer is a model built by Google. The idea of transformer basically was for machine translation. So we have an encoder and a decoder. The encoder, the task is like, for example, translate from Russian to English. So the encoder will take our Russian tokens and move them to to a space. Let's call it the meaning space. And the decoder will take the meaning from the meaning space and generate an English tokens that has the meaning of the sentence that was in the encoder. How can we use the transformer for image captioning? The same idea. We build different decoder that take the image. This decoder will take the content of the image and take the meaning. The meaning. What are the objects? What are the attributes of the object in the image, and convert that to vectors in the meaning space. And then the decoder is trying to take from the meaning space to the English language. So he will take the information from the meaning space to generate English sentences. And this is how we generate captions. Before going into the details of the transformer, let me show you the final model, so we can understand well what we are dealing with. This is the final model. So we have an image, we have the restaurant 34. The restaurant 34 will give us the meaning of the image. Then the decoder is responsible to take the meaning, the feature vector or the meaning of the image, and generate the captions. Here we need to understand why decoder can do that, and why the decoder can do it without the idea of recurrent that LSTM or the RNN has. The decoder, it has a stack of layers. Each one we called it the decoder layer. Each stack has 3 main parts: the mask multi-head attention, and here also we have a multi-head attention, and the final one is feed forward. The main idea of each one of these, the multi-head attention, it gives the decoder layer the ability to take different information from the sentence into consideration. So for example, if we have like for example, the fact that the output embedding are offset. So it should like the masked multi-head attention, it connects the word fact with the word offset. and the word fact by the word opposition. This is why we build and we connect the different parts of our caption by building an attention matrices inside the decoder layer. Then we have the multi-head attention here. This sublayer task is to give the decoder the ability to take also a parts of the encoded image or the feature vector into consideration. So the idea is that the query, these three arcs, the query, we get it from the caption sentence, and the key and the value, we get it from the feature vector. This layer job is that from the query, what information our decoder wants, it will give it from the key and the value of the encoded image. Then we have a feed forward. The transformer in general have a stack of these layers, not just one. So from these three sublayer, they are in one layer, and this layer we have it like, for example, 6 times. The attention that we have, it's called the scale dot product attention. How we attend to different part of the image. We multiply the query and the key matrices. The key matrix and the value matrices are the feature vector from our encoder, are the feature vector of the image. So we multiply the query with the key to get a weights, what parts of the feature vector we should attend, and then we weight our values. This is the attention of the this is how the attention build. In the first sublayer here, the query and the key and the value are the captions. And the second one, the query are from the captions, the captioning that we are generating, and the key and the value are from the feature vector of the image. And this is a diagram of how the attention model is working. These are the implementation, and there is an important information. It's the mask. Why here that it's a mask multi-head attention? Because we don't want our decoder to look at information that he hasn't been to the future information. This is why we just, like, for example, to generate the first word, we just look at the first part of the caption, and we ignore the rest of the information. For generating the second word, we look at the first and the second word. Like for generating the second word, we just looked at the first one. To generate the third word, we looked at the first two ones, and this is how we prevent our model to take a look at the future information. In my opinion, there is a very strong idea that the transformer provided, which is the multi-head attention. The idea of multi-head attention is, instead of building a large one-head attention that just retrain this head, we build different heads. Each head have different representation of the subspaces at different positions. How each head have this different representation? Because we initialize each head with different random values. By this way, when we are training our heads, each head will have like a different start. So of course they will have a near I think near end at the end of the training, but each one of them, he has different representation, because each one of them looks at the caption and the feature vector in different perspective. And I think this is a very powerful idea that helps transformer to like to have these. I think this different attention help the transformer to be able to, I think, like to overcome the idea of this the cell state of the LSTM. When we use the attention, as we said, in the encoder-decoder attention to help the decoder to attend to different parts of the encoder, and the self-attention to help the decoder to connect different captions. Also, we have a position-wise feed-forward network. This is this sublayer, the third sublayer. And why it's called a position-wise? Because it's like, for example, if the length of our caption, like we built, is 36, so this feed-forward will apply for each one of the 36. So this is why it's position-wise. And it has the like different parameters from layer to layer, but it has the same parameter for different positions. And also another important idea, the recurrent neural network, it can attend or it can like learn the position of the word because it's a sequential model. So the RNN knows that now he is on the fifth word, or on the second word, on the third word. But how we can provide this information to the transformer? The idea, by generating a positional encoding. The positional encoding in general, this is something like that. We add a positional encoding to different positions, like to the encode, like different position of the captioning sentence. Let me explain how. Here we have the output shifted one position at right. Later we will talk about the training, how we train this model. But we add the embedding, then we add the positional encoding. The positional encoding, what we'll add is it will add different values at the different position. This will give like a value that near each other, like it will increase the value of increase the positional encoding with the value that are near each other, and give low value, for example, here for the green line, low value for the words that are far from this word. So for each word, for example, if we have a word in the index of the word in the sentence is 20. So for near words, we have near values. But for far words, we have a low value. This is how the encoder, the transformer, take position into consideration. We built our model and we define our optimizer. The definition of the optimizer, I get it from the paper as it is. I really didn't take a deep look into it, but it's based on Adam optimizer. I think I dropped a lot, but we can skip it for now. How we train our model? We train our model by the same as training any image captioning model. We start with a start word in the output, and we tell our model to generate the first word. Then we add the word that the model generated. We append it to the input sentence, and then we tell our model to generate the third word. And so the model is autoregressive. And this is how we generate the captions. How we train our model? Each time we compare the output of the model, each time we input a caption, and the output should be a one-shifted one. This is why we get our training our training like set just for the decoder part. Here just our recursive entropy is conditional probability, not as the normal one, because we are conditioned with the feature vector of the image, also the blue score. I built the model from scratch and I trained it. It increased the cost, but Google Colab didn't give me enough time to train the model. And I found that this implementation of the transformer doesn't converge stably. Like it irritates and doesn't give a good results. So I used the PyTorch implementation of the transformer decoder layer. In PyTorch, there are transformer decoder layer. We just give the dimension of the model and the number of heads, and then we build the transformer decoder layer by telling how many layers we have. We want. I built the model. I trained it, and here are the results. For example, like this are the references captions, and this is ours. The blue score, it has a worse blue one, but better blue 2 and 3 and 4. I think this is, it means that our model generate more accurate, like in general, more accurate sentences, but sometimes it use not accurate, not more accurate words. And that's was my work. Any question?
Thank you very much, Habib. So yeah, colleagues, let's ask questions about that interesting work.
Let me ask a question about your first model.
Okay. Yeah. Can you hear me?
We hear you.
Yeah, but I can't hear the question. I don't know if he.
Dmitry, we can't hear you. Bahitov. It seems a problem with connection.
On my side, or on his side, because I can't hear you.
It seems on his side.
Okay.
Okay, so I think he will return.
Yeah. Maybe to GitHub, I think it's better to
maybe
present over here.
Now we can answer another question.
Yeah.
So I have a question. If we want to change context of generation, for example, we can generate caption in several contexts.
What do you mean by several contexts?
Well, if you show me image, I'll explain. So,
like you mean like this?
Yeah. For example, we can say that a man and the dog is standing in a grassy area, or a man take something in his hands, or
okay.
dog is watching on man, or we can just describe in general. We see trees and ground and something, so we can change.
Yeah. Yeah, I get the idea. Let me. I really didn't look into this idea, but I have a general like imagination how we can do it. When I generate this caption, I just took like each time I took the highest, the word with the highest probability. There is another way, and it's a more accurate way to use the beam search. Beam search, in general, it takes, like, for example, into consideration each time the must five words, the highest probability of 5 words. I think using the beam search, we can generate different captions for the same image. I'm not sure that these different generation of the captions are in the same context or not, but I think it will give us like more than one context. This is if we don't want to change the training process. I don't know if you got my idea.
Okay, yeah, I understand. Did you try to that beam search?
Actually, I started the code, but I didn't continue it because I didn't have time. But let me tell you, this is here. So we keep the top K value and the top K indices, but I just took the first one. So I can do it, but I didn't have time to finish it. But I plan to do it.
Okay.
Yeah.
So Dmitry Ignatov also have experience with that beam search, but
Фрэнк, я на английском не общаюсь.
Да, я понял. Ну, речь про beam search.
Ну да, я понял.
Я тоже начинал писать код и.
Ну, у нас там сложность еще в том, что архитектура немножко другая. У нас там есть дополнительные вектора памяти, так называемые, и коннект там идет от энкодера к декодеру на каждом слое, а в трансформе классическом идет из конца энкодера в декодер один связка. И то есть там такая хитрая замудренная вещь, надо разбираться. Ну, вот я пробовал, у меня не получилось.
Yeah, so we will discuss it in future, I think. So now, another Dmitry, it seems, come back, but he took, so Dmitry, you can ask the question.
Yeah, my question is about first model. I didn't get how you generate sentence because, as I understood, you train your model on tokens and how you generate sentence from tokens.
Okay. Let me explain. This is our feature vector of the image. We take the feature vector and we calculate the attention that we generate that the attention. It's called alpha attention. How can I say it? We start the generation with the word start.
Sorry.
Okay.
Attention is you mean you select
attention is this value, the weight that we should give to each feature vector of the image, to each part of the image. The attention is these values, the weights. After we get the weights,
you select the area of interest or the
area of interest. Yeah. So after calculating these weights, we have a context vector, which is the sum of the different parts of the sum of the weighted parts of the image. This context vector, we give it to the LSTM with the start token, and the LSTM should give us the first word. Then for the first word, we also generate, as you said, the area of interest for the first word, and we give the context vector with the first word, and it should give us the second word, and we continue doing that until the LSTM like one option it gets to the maximum limit of the caption, in our case 36, and the other options, the LSTM give us the word end, so the LSTM ends the caption, and this is how we stop. Yeah,
I see. Thank you.
And I would like to tell you how we can improve this model. First, there are different things that I didn't apply. For example, like I think the main improvement that we can do to this model is by using BERT. BERT for like for those who doesn't. For those who don't know, BERT is the stack of the encoder of the transformer. And the main difference between the BERT and the transformer is that it trains the encoder bidirectional. Here, in the main paper of the transformer, it's an autoregressive model. So the model can't look to the future information. But in BERT, no. It's a bidirectional stack of the encoder layer. If we use BERT for generation of the caption, we can use the embedding that BERT has. This will give our decoder part of our model more ability to generate more accurate sentences. And I think to more smart, smarter to attend to different part of the feature vectors. This is one way to improve improve our model. Also, another idea to improve our model. I wished I had time to do it, but the training takes so much time. I think I saw that different people, like other engineers, they put an encoder stack also after the ResNet, for example, here. So after the generation of the feature vector, they like the output of the ResNet, they use it as an input for the encoder of the transformer. I think this is a lot because transformer in general it's a very heavy model. I suggest to use multiple feed-forward networks between the ResNet and the multi-head attention. In this way, our model, we can get more better information from ResNet, and also we can use ResNet with fine-tuning last few layers. This I think also will increase the accuracy of the model. And that's it.
Thank you very much. It's interesting. I think if you plan to continue, we can. We have a project on that, so we can continue such research if you also have plans.
Yeah, so great.
So if somebody else could ask questions, please.
У меня есть такой вопрос. А есть ли ссылка на сам ноутбук, чтобы ознакомиться с ним чуть-чуть позже? Потому что так английский не сильно не силен. Ну, не силен, но хотел бы.
Да, я I uploaded the link to the Telegram group.
Хорошо. Или в Телеграме есть это сообщение. Сейчас я
Да.
посмотрю.
And there is also the link to the main two sources of the code and the information. The paper that Google had, and this is the annotated transformer. It's the implementation by Harvard. I get the main implementation of the layers from here, and also the images.
Thanks. У меня вопрос больше.
Okay. So Habib, thank you. Very interesting work, and I think every time I hear about transformers, I hear something new, and you have some vision that's also, I think, quite interesting. So
Thank you very much.
thank you very much. Yeah.